going to All right, this meeting has been recorded. Hello, everyone. Thank you so much for joining us today for the AIAA Los Angeles section webinar. So today we have very exciting talk and a very modern technology. And actually, it's very, very important, the combination of technology and innovation by a leader in both aspects, and a very good integrated effort. And from a good company, very exciting product. So we'll learn more from the speaker for the exciting development and the new technology. But just before that, we have a few logistic and AIAA message. So first of all, so for online attendees, you are welcome to click raise hand on Zoom. So we know we can enable your microphone, so you can speak out your question, but kind of respect the speaker and choose the right timing to ask the question. Maybe you can first ask the speaker, is it okay to ask question, or you can wait till the end so you can look at the timing. So you can type in a Q&A and chat. So speaker and I will be able to see it, but it might be good to speak out, have an interactive session. That's a good issue. And second thing is about AIAA. As you know, AIAA is a nonprofit professional organization, the #1 leading aerospace professional organization. Used to be the only one, but it's still the #1 and very high reputation. And we give out also prestigious award. For example, we just gave our Robert Goddard Award to Mr. Jeff Bezos in Blue Origin for leading the Blue Origin rocket technology and for future exciting space microgravity and Moon Mars exploration. And we have many corporate members. For you and your company would like to join, we have corporate membership, professional membership, educator, high school membership are free. Also university, and we have university student branches in Cal State Long Beach, UCLA, USC, UNLV, and our USC student, they broke the amateur rocket altitude record last year, and we gave them awards at USC. And our UCLA student, they broke the liquid rocket propulsion rocket altitude record as well. So it's a very exciting project. So and the Cal State Long Beach student, they got NASA approval for their SHOCK student CubeSat to be launched by 2028. So potentially some of the technology today, could kind of, interaction with the student. They have the CubeSat, and the CubeSat project is very vibrant in the AIAA and also Los Angeles section. In case you didn't know, recently there is a small sat conference in Utah that used to be supported by AIAA, but now not anymore. But AIAA is still giving out small satellite awards. And today's topic, you will see a lot of interest. Of course, you will hear from the speaker, especially the KA band, that's for space telescope, space communication. That's very, very exciting. And the Starlink, very many things is heavily utilized technology. So we have a great conversation today as well. Okay, so I think that's what I'm trying to kind of say logistics. So you already saw the bio for our great speaker today. Basic look, he's a field application engineer in Inferno Art and Concept. It's a very interesting. You can see, hey, he's very friendly and he's waiting there. So I don't want to repeat all the bio, but basic 2 or 3 points. Number one, he is the leader in the Inferno Art and Concept on this effort. Number two, he's a leader in both technology and innovation, not only in his current position, but also since he was in University of New Hampshire, and also previously got the student teams to won the first place, and also in another competition there in Maine, the second prize. And since student, he has been the leader in both innovation and technology. So without further ado, let's welcome Mr. Luke Conroy for the today's great presentation discussion. Thank you so much.
Yeah, thank you very much. I really appreciate the invitation to be able to speak today, and it's definitely an honor to be one of the guests for AIAA because obviously this is a very impactful and important organization, and it's really exciting that me, an engineer from New Hampshire, can speak to the Los Angeles division of the AIAA. I wish I could be there in person. I'm calling in remotely from New Hampshire today, but I think another opportunity down the line would be great. It would be exciting to visit in person. Me and a lot of my colleagues are in California frequently, so I think that would be a great opportunity moving forward. Yeah, I appreciate the introduction. Maybe a little bit more about myself. So as a field applications engineer, I've been in this role for a couple of years now with Ardent Concepts, and I basically am the technical support for the sales team and for our customers. So if any of our customers have technical questions, they'll go to me and my colleagues, and I'm frequently on calls and visiting customers just to make sure that I understand their problems, and providing the right solutions and working with them on the technical side. And then I relay all of the information that I capture to our design engineers who will actually complete the designs for our products, and deliver the final components for them. So that's a little bit about my role. Amphenol Ardent Concepts as a whole. So Ardent Concepts is how we were originally founded as an organization, but then we were acquired by Amphenol, which is a large multinational connector corporation, excuse me. And this happened in about 2018. But Ardent Concepts is still very independent. I think we still have a small business mentality, and it's been exciting to be part of this team for a while because it allows us to kind of, I think we have a lot of great innovative ideas, but we can also pivot very easily to adopt new applications to try to find new solutions for problems because we have this small business mentality. So that's a little bit about me and Ardent Concepts as a whole. So I think without further ado, we'll get into this. I will say actually before we get started, I love an interactive audience. So if you do have questions, raise your hand. I don't know if I'll see everything, but maybe I can rely on some of the help online here to maybe just pause me, and then we can get your questions read, or we can get you unmuted and you can answer. You can ask your questions. So I think I'd appreciate that. But if you have questions that are maybe a little bit more abstract or anything, we can save bigger questions maybe for the end. But if there's anything specific about a topic I'm discussing, please jump in. I'll really appreciate it. All right, so a quick agenda for this presentation. I'm just going to kind of have a quick introduction to kind of set the stage of why we're talking about what we are today. And then we're going to go into a couple specific aerospace application use cases. So these are projects that me and my colleagues have worked on that we've been exposed to. And we'll discuss, kind of some of the unique design requests and challenges that these customers were facing. We're then going to go into some of the aerospace challenges, interconnect challenges, and then the solutions for those. So there's 4 specific challenges that we're going to discuss. And then we'll kind of, at the end, kind of loop in to see how Ardent Concepts has, tackled some of these problems, how some of our solutions answer, and how they're good puzzle pieces to fit and make these systems work together. And then at the very end, we're actually going to loop back and see how everything fits back into those application use cases. So we'll just hang on for a moment. And if you have any questions, please let me know. So to start out, I think it is really important, I guess, to set the stage a little bit. We're going to be talking a lot about electronic design because I work for an electronic connector company. So that's kind of where my expertise is. But in general, whether it's a satellite, an airplane, some other system, a telescope or something, there are going to be a lot of different electronic components in this system. And I don't think none of us know everything about everything, but there are a lot of different subsystems that are very, very important. Obviously you have to have power, you have to keep your system, your plane, your satellite, make sure that it has enough power to function. do its core task, but then, still maintain enough power to travel and move. Communications are obviously really important as well. You have to communicate with your station, you have to communicate with other planes, and you have to collect and then retransmit information. So for any system, regardless of what it is, aerospace or not, communications is really important. In all electronics, you have some sort, but you have some sort of a processor, that processes all of the information, makes decisions, and then closely tied to that is like memory and storage. So you're collecting data, you got to store it somewhere for the processor to access. And then specifically for aerospace, you have attitude and orbit control, making sure you're in the right place, the right orientation, wherever you may be. And then you have to make sure, that you have an environmental control system, thermal control or otherwise, to make sure that all of your systems are at the right temperatures, the right humidities, whatever it may be. You have to make sure that everything is operating under its ideal condition. So, electronic design can be very complicated. There are a lot of different moving pieces, but that's even just, that's the surface level. Within each, you can kind of see in the middle of the slide here, with just communications, for example, there are transmitters, there are receivers, there are antennas, beamformers. You could go on and on. There are lots of different subcomponents, components, sub-assemblies that all have different functions. And the same is true with processors. You have different application-specific ICs, field programmable grid arrays, digital to analog converters, digital signal processors. You have a bunch of different components that are doing different tasks, and every single one is really, really critical. You can't have a system that is just operating with some of these. Every single component is really, really critical. But the first question that I'll ask is how do these components operate reliably, and how do they maintain their functions? And that's a really broad question. But to me, I think the answer is kind of obvious, and maybe I'm a little bit biased with my background. But they all communicate and they all operate with interconnects or connectors. So all of these different components, whether it's a transmitter or a receiver, or within a processor, a digital signal processor, these all have functions, but they have to communicate with each other. They have to be interconnected to transmit, even if it's power, they have to transmit the power somewhere. They have to transmit the memory between the processor and the storage. And so everything relies on interconnects. So when we talk about electronic design, a lot of times we're thinking about specific components because that's where a lot of the focus is. That's where a lot of the technology is. But a lot of people forget that there's a lot of important technology in the interconnect design. Although it's kind of like the, I don't know, younger brother that nobody really thinks about too much, you can kind of see here, it's all connected. So interconnects are really, really important in a system design. And while they might be overlooked, I think an important designer, a good designer will see the importance in selecting the right interconnects for the right problems and solutions. So that's kind of a quick introduction and kind of where I'm coming from today. Of course, that's my background, so maybe I'm a little bit biased there, but bear with me as we go through the rest of the presentation. So any questions so far? That's kind of vague, so I don't know if there's going to be any specific questions. All right, I'll keep on moving forward. So now we're going to cover a couple, again, application use cases that we've worked with our customers, and I'll kind of give you the background information, some of the challenges and requests that they had, and then we'll revisit it later in the presentation. So this first application use case is for a communication satellite, our customer that was developing. And specifically, we were focused on the payload processor design. So this satellite is, again, a telecommunications satellite for low Earth orbit. And this one specifically is geostationary. So it controls its orbit at it relative to us on the ground. It looks like it's staying in the same place in the sky because it's orbiting the Earth at the same speed that the Earth is rotating. But specifically, this design for the payload processor They had a couple of different requests, but its overall function was just to collect and process information. So this has, a bunch of different sensors, mostly like antennas for communication. So it receives signals in the antennas, brings this into the payload processor. This collects all of the data, processes it, makes sure that's in like a usable state, make sure that it's clean and there isn't any noise, and then it'll, retransmit it to another antenna or some other use case. But that's kind of the gist of what the operation of this payload processor was. So our customer had a few different requests. They asked for the first one, they needed some cables to go near the application specific IC, so the ASIC. They needed, some breakout to go near there on the printed circuit board, and then breakout to just like a panel that you could just, plug things into, a little bit more user friendly. So they said, okay, we need some cables to go near this ASIC to like a front panel that you can easily interface with. Next, they also asked for some kind of interconnect for a BGA or an LGA device, so a ball grid array device. And these are typically just soldered down to a printed circuit board, but they were trying to explore other options and we'll kind of get into that in a little bit. But they said, okay, we need to, we have this packaged chip, or we have this package with a chip inside, we need to connect it to our printed circuit board. What's the best way to do that? And then lastly, they had a couple different printed circuit boards in this design, as you can imagine. So they needed to have a board-to-board connection. And there are lots of different ways they can do that as well, but they asked us what we recommended. A few specific design requirements that they mentioned was one, obviously this had to be mechanically reliable. So if this is going into a satellite, it's getting launched into space. Space isn't as itself just isn't the easiest environment to operate in. So it had to withstand the thermal extremes that it'll see during launch and once it's deployed, the vibrations from during launch and as it exits the atmosphere, and then once it's in space, it has to withstand any outgassing. So outgassing is when a solid, particles from a solid turn into a gas, and then they can eventually settle onto sensitive equipment, and that's bad. So we don't want anything, releasing from our solids. A couple other considerations that they mentioned, since this is on a satellite and being launched into space, they wanted it as lightweight, as low mass as possible. Because fuel costs are obviously extremely high when you're sending something into space. And then lastly, they wanted this to be Ku, K, Ka band capable. So this is a specific operating like radio frequencies that we're seeing a shift in general in space and defense. But I believe it's 12 to 40 gigahertz. So previous generations of the satellites operated at lower frequencies, but as they shift to these higher frequencies, there are benefits because you can transmit more data, you can transmit it faster, but the downsides is you have to revamp your entire electronic design, you have to revamp the interconnects, for example. So these were some of the major design requirements that they outlined for us. So overall, I think we took this information, we're like, okay, thank you for sharing. I think we probably can, we'll digest this a little bit and we'll get back to you. So I think later in the presentation, we'll get into this a little bit more once we have some more context on, some of these design problems and really how we accomplished those. All right, so that was the first use case. I'll take a sip of water if you give me a second. All right, so another use case that a customer came, this is a separate customer, they came to us and they had an airborne phased array radar. So this was on a plane, a phased array radar antenna, and they were using this to collect storm and weather data. So actually, I feel like for me in the Northeast, maybe not everyone in California, this is pretty relevant right now because of Hurricane Erin coming up the coast now. But these these systems are really, really critical because as storms develop and as, especially major storms and hurricanes develop, we need to make sure that we have enough information about them. We have as much information as possible. So, collecting data early is really important, but then as these storms grow, having more data that we can share with, people that might be affected, people that have been affected, then learning what we can from this information and trying to use it for the future. So this data is really, really critical. And what the customer was specifically designing were these beamforming electronics that were actually placed in a container that was on the outside of the airplane. So you can kind of see in the bottom right picture, there's a couple of red highlighted areas. So that's where these electronics were placed. And they were placed outside so that they have, direct access to, best signal, best radar transmission from these locations. So this customer, they didn't have as many requests, but they wanted some cables to go from a printed circuit board to a front panel again that you could like easily interface with. But some of their requirements, which were, some similarities to before, they wanted to be low mass. They wanted to be as lightweight as possible because this is in flight. They wanted this to have a really high signal density. So they didn't want a bunch of big, bulky connectors and electronics. They wanted this thing to be small, compact, very dense for the capabilities that it has. So they wanted something with a lot of signal density. They also needed high electrical bandwidth. So this wasn't in like the K bands, or actually, I think it was the KU band. I think this was sub 20 gigahertz, but still fairly high bandwidth. And then lastly, and similarly, this had to be mechanically reliable. So it had to withstand, different thermal extremes as this is, going in the ground to flying at altitude in some colder temperatures, and it is going to be outside of an airplane. And it's going to be, have to withstand some vibrations of being on a plane, landing, while an engine is operating, etc. So we can kind of see so far, okay, there are, some key design requirements that a lot of these aerospace designers are requesting. I think logically, a lot of them make sense. And even though this is in flight, and previously we were talking about a satellite application, there are still some similarities. All right, so the last application use case that I'll touch on is for a ground-based system. So a little bit different, but again, this is for a phased array radar antenna. And this, we don't have the specific details on how this is going to be used. But their request was for a flexible printed circuit board to a PCB connection. And this was making the connection between some control electronics to the actual radiating elements on an antenna. So, excuse me, you can imagine that there's, a lot of processing, like signal generation happening on a printed circuit board, and then they have to get that information to the actual antenna. So that's kind of where this connection was happening. But then on top of this, they also wanted to be able to validate and test these different products as well. So they wanted to test the flexible printed circuit board. They wanted to test their regular printed circuit boards. So they asked if they could have some cable assemblies to break out to test equipment. But critically, they wanted these to land on the same connector footprint as the board-to-board connector. So that's definitely a pretty unique request, and not all interconnects have that capabilities. But I think it made sense why they wanted to do that. It made their design and their life a lot easier. So that was kind of where they were coming from. But even though that this is a ground-based system, they did have some design requirements. They wanted this to be really really dense. They wanted the signals to be, as tightly packed as possible so that the overall system could be a bit smaller. They wanted this to, again, be mechanically reliable with thermal and vibrations because I imagine this is going to be moving on the ground. They did also mention this wasn't a critical design requirement, but they did want this to be as lightweight as possible. So I imagine that it was on some sort of vehicle or something, that was seeing some vibration, some movement, mass mattered, but it wasn't critical. All right, so these are 3 different application use cases. I guess we'll kind of pause here before we get into some of the specific challenges and then solutions that some of these application spaces might see. Are there any questions so far? I'll wait a second. Take a sip of water.
Yeah, I think Mark has some question, but I don't know why he cannot speak out. Mark, do you want to speak out or you want to wait?
I just wanted to make sure I wasn't, I'm not an engineer, so I'm not an expert with these things, but I'm just super curious. I'll ask my second question. You were talking about thermal extremes. I'm curious about temperature cycling ranges and what you're sort of dealing with there when dealing with space. And how do your interconnect designs kind of accommodate those thermal expansions and mismatches, et cetera? I don't even know if I asked the question right, but.
No, that's a very good question. That's a very good question. So we'll actually get into this pretty soon, but I can kind of I can answer the first part of that right now. But the temperatures that we see, especially for like the space, the satellites, they can vary quite significantly. That being said, our products are usually never like on the outside of the satellite. Even for the plane, this is still in, some sort of shielded container. So typically our products are rated, we can get down to very cold temperatures, like cryogenic temperatures. But then typically the maximum temperature is usually like 125 degrees Celsius that we can operate within. But still, there's, quite a significant, there's quite a significant area that these have to operate within. And there are different like military standard and qualification like tests that these can be put up against, which again, I'll mention in a little bit. But usually for a specific application for the satellite, for example, they'll have a specific number where the customer will say, this has to operate between -80 degrees Celsius and 120 degrees Celsius. I think something like that is probably pretty typical in a lot of the applications that we see.
Thank you.
Yeah, of course. But then, yeah, this actually segues very well into kind of the next couple slides. So thank you for setting that up. Are there any other questions, or are we good to move on?
Not right now. I'll hold. Thank you.
All right. Yeah, thank you. All right. So now we'll go into some of the specific aerospace interconnect challenges that we see in this industry, and how some possible solutions for them. So the first one is all about vibrations, but also temperature changes. So thank you, Mark. So first and foremost, what we're going to talk about is solder joints. So solder joints and just like soldering in general has had a long heritage in electronic design and in aerospace design. Soldering is very, very common. There's a lot of research that's gone into it, especially with aerospace, to try to make sure that we have the proper mechanical reliability with soldering, and that these solder joints, once they're set, they're gonna stay in place and they're not gonna break or fracture or crack or anything. And I think a lot of progress has been made. A lot of different materials are used in these solder balls that are used to connect, printed circuit boards, cable assemblies, packages to printed circuit boards. So they're very, very common, and a lot of research has been done. But there is still some concerns about how well these are, how well these hold up in extreme environments, and just how reliable they are in general. And something that there are a few reasons why this especially comes up in aerospace. So the first one is the CTE, or coefficient of thermal expansion, mismatch between a printed circuit board, for example, and a package that's soldered down to it. So the picture in kind of the bottom right, it kind of shows here that as at room temperature, everything is great. Everything lines up. It's the package is soldered to the printed circuit board. All of the solder balls are connecting it. they're doing just fine. But then as you either increase in temperature or decrease in temperature, the printed circuit board might expand faster than the package or vice versa. And if that happens, sometimes that can put strain on the solder balls, which are holding these two together. And then that can result in fractures within the solder balls. It can cause them to totally break. So that's a problem that we're seeing. But especially this is a problem that we're seeing more and more as these packages are getting bigger, chips are becoming more powerful, and they have more inputs and outputs. So the number of solder balls for a given use case, whether it's a given soldered chip or package to a connector assembly, these are getting bigger and bigger because there's more inputs and outputs, which is great. There's more data being transferred. But as these get bigger and bigger, those differences, even if it's the same temperature difference from 0 to 100 degrees Celsius, if it's happening over a larger area, the relative contraction and expansion is larger. So then that's causing even more strain on these solder balls. So that's one issue that we're seeing increasingly more and more. Another issue, which is, it's always been there, but it's just the fractures because of launching these into space, whether it's on a plane, but especially, if this is going into space itself in a satellite or missile or something else, there's a lot of vibration, a lot of stress, and that can cause these solder balls to break for bigger packages too. And just, of course, mechanical stress from these systems bending or warping or anything like that, And as these are getting bigger and bigger, the warpages, the stress vibrations, more than likely, at least one of these solder balls in a really big, multi-thousand connection package, one of those is going to break. So that's a problem that we've seen a lot in our industry as a whole. So we'll talk about a solution that can help here, and that's solderless and compression mount interconnects. So solderless technology helps deliver a more reliable connection because there isn't a permanent connection. So a solder ball, when you solder it, you heat it up, you melt it, it sticks the package and the printed circuit board together. But for a compression interconnect like a pogo pin, it's just sandwiched in between a package and a printed circuit board. And because it's just sandwiched there is no permanent connection, it can compensate a little bit more for vibrations. It can compensate for movement in the X and the Y direction for the CTE mismatch because those pins just slide. So it can compensate for up and down, but then side to side in both directions. So that's one, theoretically simple solution for solder ball and solder joint failure. Furthermore, to add a little bit more context on how this is used, so it can be used for a lot of different things. I was mentioning, packages, BGA packages with 1,000 or 3,000 different solder balls on it. So you can have pogo pins that just mate directly to those solder balls and then mate to the printed circuit board. So they're like an interface between the two. But you can also have compression mount board-to-board connectors. So, the problem statement is still the same. If there's vibration due to a launch, it's still maintaining a connection between two printed circuit boards. And for cable assemblies as well, if you're soldering cables directly to a printed circuit board, with everything going on, some of that solder could crack or break. But if it's all compression mount, if everything is held and screwed together tightly, it'll maintain a connection even if there is still some movement. So overall, they can help deliver long-term reliability in these harsh environments, whether it's due to thermal effects, mechanical effects. Solderless and compression interconnects are a really good solution for that overall. All right, I'm going to move on to the next challenge now, and that's design density and mass. So kind of like I was talking about earlier in the beginning of the presentation, electronic systems, they're just getting more and more complex The designs are getting more complicated, which is, you know, exciting. We're able to do a lot more than we used to be. And with that comes a lot more data. So there's a lot more data being exchanged. There's a lot more data being collected. But then everything has to get, you know, processed more. It has to take up some physical space. And on top of this, a lot of electronics are getting smaller and smaller, which is again really exciting because we can pack more, you know, we can pack more power into a given chip, into a given processor. But then, okay, this is great. You have a super powerful processor that can handle and, you know, process a bunch of information. But then what do you do with it? You have to, that information has to go somewhere. And if you just use a traditional, you know, regular single SMA cable, for example, or just, you know, a regular old connector, you might have a problem because you can't get that information out to all of these, you know, big bulky connectors. So you need something that has a really high signal density. You know, it can carry a bunch of inputs and outputs in a small area. So we've seen that overall is as these systems are miniaturizing, there's been a demand for the miniaturization of interconnects and making those smaller. But even on top of that, and especially with aerospace, you know, you also want these to have a low mass. You want them to be lightweight because they're being launched into space. And of course, the heavier something is, the more fuel you have to buy and then burn to get those into space. And now, especially, there's a lot more competition in the aerospace industry. So cost is even more of an issue. You know, there are a lot more cost pressures than there might have used to be, than there used to have been. So, you know, we really need to make things small and we really need to make them lightweight. So that's another problem that we're facing in partially just the overall electronic semiconductor industry, but also in aerospace as well with the mass aspect of that as well. So that's the problem. What do we do? I think I kind of hinted at it earlier, but you need high density interconnects. So you need a high signal density to enable the miniaturization of these small electronic components. And you know, you need to break out all of those signals, even though they're really so small and powerful. You still need to break those all out. And you know, the added benefit of high density interconnects is that they are smaller in size as well. So they typically decrease the mass of the interconnect, but they might help decrease the size of a given design. So it might miniaturize an overall system within a satellite, within a plane, or something. So I just have a couple examples here. I like the top right and the bottom left. Are just like some individual cables. So the top right will look at some individual, those are just like SMA coaxial cables versus a gang solution. And then on the bottom left is, I think, yeah, 16 ganged coaxial cables, and then the equivalent spacing that you would need to break those out for a single-ended individual solution. So you can see there's definitely added benefit to the miniaturization of some of these designs. And yeah, I guess I kind of already hinted at this with the cables. But then furthermore, so that's kind of all on the cable aspect of it. But then as the specific components and packages are getting smaller, you need to ensure that you can, you know, handle those as well, whether it's even if you're just soldering it, you know, making sure that you have the appropriately sized solder balls, or if it is an interconnect, you know, like a compression mount interconnect, you need to make sure that the contacts, or whatever is making the connection between the printed circuit board and the package is small enough, you know, so that we can accurately land on the pads on the printed circuit board and create a small enough footprint. So that's kind of what this image is showing. In the center there, you can see the big 4 holes, and then in the middle is a bunch of little pads that you know, some kind of FPGA or some package would mate to. So enabling, you know, the miniaturization of those as well is really important beyond just the breakout cables. All right, we'll take a sip of water before we dive into this one. So another aspect, challenge that we've seen recently is SATCOM, but aerospace in general. They often draw inspiration from commercially available interconnects. I think a lot of times big corporations, especially with AI nowadays and everything, people are dumping a lot of money and investment and focus, I would say, yeah, and focus especially on these commercial solutions. And, a lot of times that's, getting the brand new shiny bells and whistles because, the commercial space is a very competitive landscape with AI. There's a lot of investment. But then aerospace and, like SATCOM, for example, they see all of these interconnects and they see this new thing. And they want to then incorporate them into their systems. There's benefits of using this and that technology in their systems. However, what is often not accounted for is that those aren't designed for harsh environments. They're not designed for space. They're not designed for flight. So then you have to do some customization, to make sure, or at least some qualification to make sure that they can survive those environments. Vacuum, extreme temperatures, flight, kind of like I mentioned. So what you need to find then as a possible solution is you need to find, either just something that is already rated and qualified for those environments, or you need to find someone with, or some vendor with a heritage of customization, and is willing, is willing to customize materials, for example, to help enable your system. So a couple, material customizations that we often hear about is one for outgassing. Like I mentioned before, we need to make sure that any sensitive components are protected when they're exposed to vacuums or partial vacuums. So you have to select, all of your materials have to be carefully selected to make sure that they don't outgas. And then furthermore, on top of that, you need to make sure that you have lightweight components and lightweight materials too. So, if you have any metal components, substituting stainless steel for aluminum or for titanium, that's just an easy example. But some of these customizations can get very, very specific, based on the specific design requirements that a system may have. But then on top of that, beyond just material customization, sometimes it's necessary to customize the physical shape of a connector or of a design in general. Of course, this can be done to minimize just the mass and the size of it. But then also, a lot of these systems are really, really complicated. They're very complex, they're very small, they're weird shapes because they're fitting into a small CubeSat or something. So we will have to customize each and every component. Maybe not each and every, but the customization can help each and every component to make sure that it easily fits into a system and integrates well. So customization is another issue that we hear about a lot, and our customers often ask of us. And then lastly, the fourth and final design challenge that we'll discuss is the RF signaling, so the radio frequency signaling, and some of the changes that we're seeing. So the namesake for this presentation is the shift in the radio frequencies towards the KU, K, and KA bands. I love this graphic here that kind of highlights that a little bit more. But that, ranges from 12 to 40 gigahertz. And we've seen a lot of space and defense customers shift to this band. The increase in frequency, helps them with more and more data throughput. You can transmit more data. But there are, of course, challenges with that as well. As you increase your signaling frequency, often the effects, the interference can become more and more of an issue. The noise can be more and more of an issue. So you have to make sure that these are properly shielded, and the signal integrity of all of your electronic design is carefully considered. But overall, all of this is driven by the demand for higher data throughputs. The communication satellite that I mentioned in the beginning, more and more data is being transmitted by the minute on our world. So there's always going to be demand for higher data throughputs. But as a result, we have to hold ourselves accountable and make sure that all of the electronics that we design can withstand it and transmit that data accurately. Okay, problem. We need some high quality interconnects and electronic designs. What are the solutions? So first and foremost, and this is kind of obvious, but we need interconnects that are well designed for the 12 to 40 gigahertz bandwidth to deliver, reliable data across the systems. Something I also didn't directly mention, but also the modulation of the frequencies is also important too. So as you increase in frequency, you can deliver more data more quickly. But then also how you modulate the signals. So you can consider just like if you think of a 1 and a 0, NRZ is either, it's either a 0 or a 1 for a given like signal voltage. So, yes or a no. You can also modulate that signals to have 4 different levels. So rather than just 1 and 2, you can have some intermediate voltage steps. So for a given wave on a signal, you can transmit more data, but as a result, it's more susceptible to noise. So there are trade-offs for both, but faster operating frequencies and different modulation schemes like PAM4 and PAM6, which is pulse amplitude modulation. That also enables more data, but it can enable fewer physical channels in an electronic design, but you're transmitting the same amount of data with fewer channels, which might help decrease mass of a system, size, and cost. So these are some of the driving factors, causing the demand for this. But you need to make sure that you have good signal integrity, that your electronic designs can actually hold up to this. And furthermore, not all of the interconnects are made the same, or not all of the electronics and packages are made the same. So it's imperative that these are qualified for harsh environments when used in space and in-flight applications. So they have to be, withstand radiation, EMI shielding, or electromagnetic interference, shock, vibration, high and low temperatures like we talked about. So how do we know that these can survive these? Often we get asked about qualifications. So there are standard qualifications that we can subject our electronics to. And then also some customers will have specific requirements that we then have to go test against to make sure that they can survive. So those are some of the 4 big challenges that we see. Again, to quickly summarize, I'll scroll back. So solder joint failure, what can we do? We can use a solderless connector that can compensate for some of the movements and temperature changes. Design density and mass, we need things to be lightweight and small. What do? We make high density interconnects. We gang them together, make them as small as possible to, decrease the system size and therefore its mass. Customization. There are a lot of good products out there. Not all of them are made for space and defense. You need to make sure that when you're customizing, you properly select the right materials for outgassing and mechanical reasons, and make sure that you can actually physically fit them into your system so they integrate very well. And then lastly, RF signaling. We're shifting to higher frequencies, and there are more and more effects that we then have to consider. What do? Carefully select your connector to make sure that it can withstand that, and make sure that they're qualified for these harsh environments and they still survive. They're still reliable in these harsh environments. So that was a quick summary, maybe a longer overview of some of these challenges and solutions. Do we have any questions now? All right, we'll keep it moving then. So now I'm going to talk about a little bit about Ardent concepts and some of our technology, some of our core IP, and then how it relates to some of these application use cases to tie it all off again. So Ardent concepts as a whole again, we were founded before we were part of the Amphenol Corporation, but these 4 pillars have always been true and still stand true to this day. So first and foremost, we take pride in trying to deliver the best possible signal integrity in all of our designs. So interconnects, as we learned in the beginning, excuse me, are very important, but they're not important if they don't work. You know, you have to make sure that you're delivering the best possible signals, the best fidelity possible, you know, from point A to point B. A solderless electrical interface. Originally, we recognized the value for solderless designs. Not for aerospace or for harsh environments, but for reusability. So we wanted to be able to reuse connectors to, you know, be able to move things around, reuse them to decrease costs, you know, long term, to be able to take apart systems and then, you know, repurpose them and put them back together rather than just throwing them out. So that's why we initially developed a solderless, you know, and focused on solderless interconnects. But then we quickly realized, you know, there are a lot of other advantages that these that a solderless design has, especially in military and aerospace. Signal density has always been a focus of ours as well. You know, we recognize that as you know, systems are quickly miniaturizing, and we need to be able to keep up with that, and we need to break out all of these high-speed signals from these super dense tiny chips. So signal density has always been a focus of ours as well. And then lastly, mechanical reliability. We wanted to make sure that we could deliver connectors that could be mated, you know, thousands of times. They could be used in, you know, originally developed for just test labs, but they were, you know, reliable and easy to use. But then that's quickly translated into use in harsh environments, you know, space, vacuum, cryogenics, you know, thermal cycling. So we've expanded that quite a bit from once we started, but these 4 main pillars have always held true to us. So with all of that in mind, what the heck do we even do? So our core technology are in these kind of unique pogo pin contacts. So these, although they look really big on your screen, are really, really tiny. If I held them up, you wouldn't be able to see them. They're like, some of them are like literally the size of a grain of salt. That's how small they are. You need like a microscope to see them. So these are really, really tiny springs, but they have a very important role. So they were designed to replace a traditional pogo style pin, which is basically like a pin and it has another pin at the bottom. And then usually they're connected somehow with a spring in the middle so that they can compress. So we designed a pogo pin with the intention of trying to make it simpler and shorter, and I'll get into that for a minute, but simpler, smaller, and, you know, even better than before. So we decided, okay, to make it more reliable, to make it simpler, let's get rid of the multiple components. We'll just make a single individual spring. And even though it's shaped like a spring, it's very, very small and short, so that when an electrical signal goes through it, all of those coils, they short on each other. So it just creates a short from point A to point B. So it actually creates a really good electrical path for some of these high frequency signals. And then the Connect R is kind of a different flavor of that we developed a little bit later. But this was designed to be a little bit more cost effective. And it was actually designed originally for aerospace in the first place for some high volume programs. But, you know, kind of the same idea, a solderless, mechanically reliable compression contact. So, okay, that's great, but how do you use these things? So we use them in a couple of different ways. One is in the cable assemblies that I've kind of been highlighting pictures of throughout my presentation. And these are called the TR Multicoax, or TR stands for Terminator, but that was licensed, so it's spelled a little bit differently. But we shortened it to TR. So TR Multicoax is a ganged cable assembly. So a bunch of cables, you know, pressed into this block. And then what we have here, you can see on the top left, are the actual springs. So those are attached to the bottom of the cables. And and they just, literally one of the legs touches the cables, one of the leg touches your printed circuit board or whatever you're mating to. So that's kind of how these cable assemblies work. But overall, some of the highlights and how they solve some of the challenges, they're totally solderless. So you can, great if you're using them in a lab, you can reuse them and move them around. But in in space and defense and in aerospace, they're great because they eliminate solder joint fatigue. They can withstand vibrations and thermal contraction. So that's really great. We also have some military standard qualifications that these have passed to show that they are reliable in harsh environments. They're since they're a ganged assembly, they're very small. We also have the right angle, which I was showing you, so it can fit underneath and in tight spaces. And we can customize the materials, to ensure that it's lightweight and can withstand like outgassing, for example. Okay, so that was a lot. Now we'll go into kind of the other flavor of our product, are our sockets and interposers. So rather than connecting these to cables, these are literally just springs that are then sandwiched between either two printed circuit boards or like a device, like a packaged device, like an ASIC or an FPGA and a printed circuit board. So they just simply make a connection between two different things. But these have a lot of the similar design characteristics. They're solderless. We've put them through some military qualifications. They're very small and dense. We can customize them, both the materials that they're used and just like the size and the shape of them. And we have a lot of just design experience. Ardent actually started out only making these sockets, and then it kind of grew from there. So those are a quick summary of some of our products. And then now we're going to loop back into those application use cases to finish everything off. Any questions before we get into that, or does that all kind of make sense? All right. So before we get into that, I will just kind of highlight a little bit. So where do our connectors fit? Where does my experience lie? So I kind of hinted at this earlier. In a processor, in a payload processor, in a satellite, for example, there's a lot of electronics, and these are within a satellite, within a system. They're well shielded, well protected. So that's where a lot of our technology lives, both cable assemblies and sockets and board-to-board connectors. And then also in some of the antenna arrays where there are some other electronics, but again, these are well shielded and well protected. There are, connectors and other interconnects and electronics that live outside of those areas. But we aren't designed for like the harshest, we're not designed to be outside of your satellite connecting two different things. It can't survive that. So that's not where we're going to talk about. But there are other solutions out there if need be. All right. So coming back to that first use case, with the payload processing satellite. So again, the satellite, they had a couple different requests for this processor. How were we able to help them? We actually had a few different solutions, which was really exciting. So we used that TR right angle cable assembly first and foremost. So that mated on a printed circuit board close to an ASIC, and then those cables then went to a front panel and then like kind of mounted in a panel that then somebody could easily interface and use. So that was one of the products that we designed into this system. Another product is the SK series socket, which you can see on the top picture, the green and black. So that was a socket that it interfaced a few different BGA and LGA packages, including an ASIC. I think there was also some FPGAs. So a few different packaged devices that then were put in this compression interconnect and then connected to a printed circuit board. And again, the customer could have just soldered these directly down, but they recognize that because these are so big, the solder reliability is a challenge, and they wanted to make sure that no matter what, we maintained a connection. And then lastly, we used one of the interposers, which is similar to a socket, for a board-to-board connector, so just two printed circuit boards. And overall, they selected that because, one, it was really short. It was, very, very small, but also, again, it could withstand the reliability, or it could withstand the vibrations and the temperature changes, and was a reliable solution. And lastly, I didn't touch on it, but all of these are rated for the KU, Ka bands. So they were high frequency interconnects, well suited for some of these high frequency operations that they were undergoing, on top of a lot of the mechanical reliability and some of the customizations that we did for the materials and outgassing and low mass. So overall, this was a really exciting project to be a part of, because they were doing some cool stuff, but we were able to see a lot of different aspects of the design, and I think we provided a lot of value add, which is really, really exciting to see. So right now, the status, I think these are all fully qualified, and I don't know if they've been deployed into space quite yet, but there is like a flight schedule to do so. All right, the next project, the next use case was the airborne phased array radar for that storm chasing plane. So we ended up using, again, the TR cable connector. We went from the board to a panel that, again, these panels were mounted so that a user would interface and plug in different cables depending on whatever they were doing. But the advantages here were, again, low mass, high density. Having all of those cables in a small area was really important to them because this shielded container was pretty small. It was high bandwidth, so the high frequencies was no problem for these cables, and we had them qualified for a few different military standard, which is like a standard qualification that we were able to show them right away. And they said, okay, we trust that this thing is going to work. We'll do a little bit more testing on our side, but everything worked out very well. So these are also qualified, but I don't think they're in use quite yet. But another exciting design, very unique design. Never knew that there were planes that flew into storms to track and collect data, but really cool to learn about. Really, really interesting stuff. All right, and then last but not least, it was that phased array radar for some ground-based system, probably mounted on some vehicle. And this was, again, a very, very interesting design because they wanted a board-to-board or a flexible printed circuit board to PCB connector. That was pretty straightforward. Okay, we were able to do it. It's called the AIAA, but it's like an interposer. But that was relatively straightforward. But then the challenge here was that they also wanted a cable assembly to mate to the same exact footprint. So you could take off one of the interposers and put a cable assembly there. And, we were able to do it, as you can see in the bottom right corner, the cables on the right, and then the interposer on the left. But it was, very, very unique. And I like the picture in the top right, actually, that kind of shows where the cable assemblies fit. So you can test the printed circuit board, you can test the flexible PCB, and then you can assemble it all together and use it in the system. But the advantages here were obviously that customization to be able to do the interchangeability, but the small, dense footprint. We had qualification reports for harsh environments. And I didn't really mention this too much, but being able to customize the actual layout of the connections was really important, because in a big phased array radar, you have a lot of repeated, you have a lot of mini antennas that make one big antenna. So to have a solution that is designed to just scale and tile, so you can just put a bunch next to each other, was really important for this customer. So that's what we did, based on their spacing and their requirements. But yeah, overall, those were the three use cases that we're all a little bit different. There's a ground-based, an in-flight, and a satellite. But a lot of them have similar challenges, harsh environments, lightweight, high frequency. So that's kind of why we were able to help these customers, deliver a solution that was, has been qualified and hopefully in all of these cases work very well once fully deployed. All right, so that's the end of my presentation, but a quick summary overall, a couple keynotes to take home as you go about the rest of your Saturday. But first and foremost, maybe I'm biased a little bit, but interconnect design is often overlooked in the overall electronic systems, but it is really, really important. I tell all of my friends and family that I work with connectors, and people just kind of look at me with a funny face, but they don't understand that it is really, really important for everything that we do, everything that we interact with. In the space and defense and aerospace market, there are a lot of different design requirements that need to be carefully considered and balanced. Whether these are, lightweight or whatnot, all of these systems are very, very complex. But there are lots of different challenges that have to be considered. Is this going to be able to withstand the harsh environments? Or if I use solder, will that be reliable and will that hold up? It might in some cases, it might not in others. Design density, do I have to miniaturize this design as small as possible? Does it have to be as lightweight as possible? The material and mechanical customization. Do I need to use any special materials? Do I have to customize the size and shapes that it fits into a system? And then lastly, overall, what's really important with all interconnects is the signal integrity. How can I make sure that the best possible signal is getting from point A to point B as things get faster and faster, as things get more complicated? So there are a lot of challenges that you have to balance, and we definitely understand that. But the selection of the proper interconnect, the right connector, the right electronic, whatever it may be, for your system, as long as you carefully consider its environmental, its environment, as well as just the overall mechanical and electrical design. Choosing the right one will result in a successful deployment, whatever the program is. You just have to, consider all of your options, keep an open mind to new technology, come to stuff like this so you can learn a little bit more about some of the challenges and solutions out there. And overall, I hope that it'll all work out for us. All right, so that is everything from me. Thank you very, very much for the time again. We'll go into a question and answer session next. But yeah, I really appreciate the time to be able to speak to you. I hope that next time I'll be able to come out to LA and do this in person. We'll have some more user engagement. I don't know if I'll be able to pull 120 in-person guests, but I'll do my best to try to get as many people to come. But I really appreciate the time speaking with you this morning, or I guess this afternoon now, but thank you.
Yeah, thank you so much. This is really amazing. Can you hear me okay?
Yes, I can.
Yeah, this is amazing talk. As Mark just said, there's so many questions. This is so exciting. First, I saw Robert online. He has a question. So Robert, do you want to speak out?
Yeah. Luke, very fascinating talk. What metal is used to create those miniature springs that you're talking about? What are they actually made out of?
That's a good question. So there are a couple different ones, but typically gold-plated beryllium copper.
Gold-plated beryllium copper. Okay.
Yep.
I was wondering
Beryllium
if it was gold.
Yeah, beryllium copper has some good mechanical characteristics for the compression of the springs. It gives us a good balance of mechanical reliability, and it isn't, it's soft enough where it can be compressed, but isn't too hard. And then the gold plating, helps with the electrical interconnect. Yeah.
Okay, so the beryllium copper is to make it springy. Okay.
Yep.
Cool. Thank you.
Yeah, of course.
There's another question. Parse. So let me enable his microphone. 1 second. Parse. Let me see. Parse. Okay, Pars, your mic is enabled, so welcome to
Yes.
speak out.
So I have studied the satellite communication, and I am more focused in the power system area. So I know that they have a power transfer. There is a transfer power and the receiving power. So other than the solar panel, is there any other way to generate the electricity in the satellite? I'm wondering
That's
that.
That's a good question. I don't know if I will say I don't have the expertise to answer that well. Yeah, solar panels are the ones that I'm aware of, and I think are most commonly used. But I don't know what the other options are out there. Maybe there are some, but I don't know. I'm sure you could
Because
find something if
because there is like possibility to meet the meteorites and other solid structure around the satellite, and that can damage the solar panel, which come out
Mhm.
that no electricity.
Yeah. No, yeah, it's definitely a problem. You never know what's going to happen in space, and I don't know. Like I've been saying, it is a harsh, and I mean that with all the meaning of the word. It is a harsh and dangerous place out there. So yeah, you never know what's going to happen with your solar panel arrays that are stretched out far from your satellite. So I don't know.
Mhm.
I'm sure there are other solutions out there, but you're gonna have to dig into that one for me. If that sounds good.
Okay, then I'll connect on LinkedIn and we'll find something on the solution.
All right, that sounds good.
Okay, see you. Thank you for answering.
Of course, thank you.
Yeah, folks online, if you have more questions, please welcome to raise hand so we'll enable your mic. So actually, Paris just mentioned a good question. So you are saying that this your technology is mostly the best used for signals, but not actually for power transmission.
Yes, exactly. Yeah, that's a good point. Yeah, so we're not designed for like high power. It's mostly for like high frequency, like low current and voltage signals. Um, Sometimes for like those sockets with like for a package, there is some power that has to go through those. But even for like a lot of these, this is a little bit different, but for like a lot of these big AI chips, they require a ton of power, but our sockets don't really make sense because they're not designed for that high power. So yeah, good clarification. We don't do a ton of power stuff, mostly just high frequency signals.
And so actually, parts actually touch another interesting issue is the length of your cable. So for example, for the signal, the best optimized is certain length limitation for your technology for your cable.
Yeah, it's a good question. I would say usually, I don't know if there's a right and a wrong answer. So like for those cable assemblies, we can make them really, really long. In some use cases, for really, really like, I don't know, sensitive signals that have to be really, really weak, on purpose, they're actually, designed to be like 5 feet long. But that's typically like the maximum we'll go, because again, these aren't high powered signals like that you'll see on your telephone lines or something. These are, pretty small, well controlled. The fidelity of those signals is very important. So usually we try to keep it as short as possible. So most of our cables are like 6 to 12 inches, but we can make them longer, but not too long.
Yeah, and actually, I think there's a lot of great application in the future for your effort in technology. And you mentioned several application. Actually, if you notice, there was a news a couple of months ago. I think some company was trying to build a data center in space. So
Yeah, I've seen that.
yeah, I see. I think there's a a lot of business waiting there and technology development. So related to this, because I think there's getting, you mentioned PGA, LPGA, FPGA, BGA, so do you require any special requirement for the board itself, the printed circuit board, PCB? Do you require any special hardness or some kind of layer requirement? And I think this is related to the issue, for the CPUs, LGA, they have some kind of, latch, put pressure to put a
Yep.
contact. And for your technology, very nice, coil, those things. Do you require certain kind of pressure and like a, to hold it on the certain? Yeah, that's a good picture.
Yeah.
Do you have?
Here. Yeah, I'll start with this picture. It's a very good question. So we'll look at this socket footprint that's kind of in the center of that printed circuit board, which is like the grid array, the square. So those are all individually plated pads on the printed circuit board. So the PCB will get manufactured that way. And those pads we require to be gold plated. So usually it's like a hard gold. Some other common platings are like ENIG or INIPIG plating finishes for those pads. So that's what we require just on the printed circuit board. And same for our cable assemblies too. You can kind of see a custom cable assembly up in the top right, but that rectangle, I don't know if you can see my pointer or not, but that's also, has the
Yes,
gold
yes,
plating
yes.
on it. And then, yeah, to require these springs do have to be compressed in order to make a connection. So then usually underneath the printed circuit board, there's like a stiffener plate of some kind. And then on top of it is like a lid that then either screws into or latches into with a lever or something so that it actually delivers the final compression. So you can see in kind of this image here, you see the PCB at the bottom, the orange, like rectangle or I don't know, square X shaped design. That's the interposer. There's a guide plate, which is gray. That's also an X shape. Your actual package, whether it's, I don't know if that's a CPU or something, and then the lid on top that screws it all together. And then there are some other requirements that we have for the printed circuit board. So we recommend certain thicknesses. Like I think it's typically we want it to be like 0.76 millimeters thick or more. I think that's one of our, but it depends on the application and the design a little bit. But yeah, we can definitely work with customers on specifics.
Yeah, very good. Because I think I have some kind of idea. Of course, we'll work out some of the reimbursement for you coming here. But I have some idea for kind of demo thing you can do when you are here for a visit. I think it's very interesting, important. So while we're waiting more people, to ask question, you mentioned about several things that remind me several kind of similar technology on the ground. So maybe it's a stupid question, but maybe I just throw it out. Maybe you can help me or help people to kind of. I kind of recall some similar technology. For example, you are transmitting signal and high frequency, but that immediately remind me there are several things like fiber optics, and you
Yep.
can also these days you have like wireless transmission. Instead of
Mhm.
cabling, and you transmit the signals through wireless communication
Sure.
between board or the component. The third technology is the strip line. So instead of
Mhm.
using cable, you do the PCB, purely everything on PCB is lighter weight. And the one
Yeah.
thing I can think is the bigger PCB requirement with a cable, because of vibration, launch process or whatever, or things in space, and the cable might pull the PCB board. The
Mhm.
CPU, when you mount it, and you don't have that kind of pulling strength, but you have a cabling that might have the pulling thing. So how would you comment on those, wireless transmission, fiber optics, strip line, because they are also, moving into high frequency area. So can you
Yeah.
have some comment on that advantage of your technology? Yeah.
Yeah, definitely a good question. So I'll start with the printed circuit board, just like the strip line traces to start. So yeah, I mean, a lot of our customers have, some sort of trace on a printed circuit board, whether it's long or short is up to them. But one of the downsides of that is, you're right, it can be, lighter than a printed circuit board, for example, but those are typically very high loss. So like an inch of PCB trace, the signal loses a lot of strength and power as it goes, over that 1 inch, for example, compared to 1 inch of cable where, it'll lose a lot less power. So over long distances, it makes sense to use a cable rather than a printed circuit board trace. Also, in a lot of these systems, you don't want to have, a big printed circuit board if you're trying to span between two things. Sometimes a cable is just easier it might end up being a little bit lighter. But yeah, and even just like the mechanical reliability, you don't want these boards super, super big. Fiber optics, that's another good one. So yeah, a lot of times we see fiber optics in like data centers with a lot of just like a lot of data traffic. And fiber optics is typically used over long distances because it is very fast. But the downside of fiber optics is that it can be very power hungry. So they have to take all of these electrical signals, they have to convert them into light signals, transmit the light then travels along the fiber optic cables. And when it gets to the other end, you then have to process the light, turn it into electrical signals. So that they can, for one, just be expensive. So usually for short distances, it doesn't make sense to have fiber optics, but long distances, maybe if we do data centers in space or something, yeah, I could see that being a possibility. And then I forget what your last one was. Wireless. Yeah, so wireless, it's a good point. We're very familiar with everything becoming wireless these days. But for a lot of these connections that we make, the cable assemblies offer less noise from point A to point B than a wireless signal, because you have to transmit out the signal, and then as it's in the air, it can get affected by noise and everything, especially in space with radiation or what have you, other interference. And then the receiver then receives that signal, but then really has to clean and process it, on the other side of it. So if you're just going a short distance, a lot of times, again, short distances, it makes sense because you want a clean signal from point A to point B. You don't want to have to, process it, do any extras like inputting any extra power. You just want a clean signal from point A to point B, then a cable makes sense. But if it's long distance, then maybe wireless might make more sense.
Yeah, I agree. The signal integrity, clean signal, the wired is still better. It's still good. Yeah, this
Exactly.
is very good. Yeah. And you mentioned the outgassing. So, and I saw your cable has some kind of, plastic, protection outside.
Yep.
So have you considered, special design material to prevent outgassing from those?
Yeah, definitely. So, yeah, I guess I don't have a slide in this presentation specifically for it, but yeah, outgassing is definitely one of the biggest things that we've seen and had customer requests for. Most of our standard materials are typically okay. So like for our socket designs, for example, Ultim 1000, which you can see at the top here, that's a plastic that we use to basically contain the little springs. So that actually has really good outgassing characteristics. But for the cable assemblies, let me see if I have a picture here. I don't have a good one, but I can kind of highlight it here. I like this picture. So you can see in both of these cable assemblies, there's a little green shrink tube on each cable. So that's just like a shrink tube to prevent the cables from being like over torqued or kinked or anything. But that's actually one of the first things that we have to switch if there is an outgassing requirement, because that, I think it's the dye in it, or maybe it's just the material that does outgas. So then we have to change it to a different shrink tube, basically, that doesn't have the dye, so it's totally clear. And I think it's a slightly different material as well, so that it doesn't outgas. The cables, the blue cables that we use, those have a Teflon coating on them, and those are usually okay. But then even like the materials too, we even the metals, excuse me, we have to be cognizant of the metals that we use, because some metals outgas more than others.
Yeah, excellent. And actually, this picture actually remind me of a question, because you show your product have how many? 1, 2, 3, 4. Well, anyway, 8 channel, 8 cables,
Yep.
8, 9. So are you also trying to increase the number of cables? I mean, the density of the cabling. Is that the direction?
Yeah, that's a very, very good question. So yeah, typically, yeah, I guess we kind of answer that in two ways. we have our set like channel count. So usually 6, 8, 16 are like the go-tos. We have a 24 channel. We have made a 32 channel, but usually that's just like really big and people don't usually like using them just because they're kind of big. And then as you get bigger and bigger, sometimes the signal integrity can get affected because you want to make sure for a compression contact, everything is making a good connection. And it's easier if you just have a few channels, but as you try to make 100 connections, it's difficult to make sure that each and every one is, delivering the best signal possible. But then on top of that, we are trying to make these even denser as well. So right now, these cable assemblies, for example, you can kind of see in the bottom left image. For each cable, you can see at the bottom, there's the little, circle of where the cable connection would be made. But that spacing is actually limited just by the size of the cable itself. So the outside of the cables are touching, but we can't get them any closer than that. So we've developed some solutions with even miniaturized cables compared to these ones, even like they're even thinner, so that we can squeeze them even tighter together. So again, we've developed that. A lot of people they were asking for it, and then they realized, oh, maybe we actually don't need that anymore. We can get away with the regular ones. So we haven't sold a ton of those, but yeah.
Yeah, I completely agree with you. You mentioned there's a mechanical, there's a density. I think that's the best way is to have a in-person demo. People can pull it, touch it, and they feel,
Yeah,
wow,
totally.
this is so rigid. So I think that's the best way. But this is today's a good beginning. I have a lot of questions, but there's one more thing you mentioned. The many exciting thing about the AI chips, different thing, and they use. LGA, a lot of they use LGA, or different
Yep.
kinds of things. So, so you kind of say mention one of your product. It is my understanding is kind of adapter type, right? So you don't require those chip company to specific use your design for your special IP, connector. You can use any of the commercially how do you say over the the counter
Over there.
and it just can apply on your socket and you will connect to the board using your this proprietary connector, right?
Yeah, that's a very good question. So yeah, I guess our business model is a little bit different than others. And that kind of like I was saying in the beginning, we still are very much a small business where we have the flexibility to kind of shape, and we have the mobility to select and change our designs and our technology. So a lot of our stuff, and I guess actually this is a good slide to be on, is very customized. So a customer will say, hey, I have this chip, this AI chip, this processing chip, this whatever it is. It is this size, it has this many pads, make a socket for it. So then we'll take their design, create a custom solution for them that then, we provide to them. So a lot of our like socket designs are, I would say probably 99% of them are custom. And the customer will just buy a few of them, or, I don't know, maybe like 10 or 20 of them. And then, that's fine. Of course, there are some higher volume ones for some of these like satellite designs. But yeah, typically a customer will give us, their design requirements, their chip, and then we'll make the technology around their design.
Excellent. And well, I certainly think you mentioned your cable material, some of the material is beryllium, right?
Mhm.
Actually, just for your information, James Webb Space Telescope, right?
Mhm.
And the mirror material is beryllium, and they
Oh,
were made
really?
here. Yeah, and actually, NASA has a documentary film. This is not top secret. It's NASA stuff. And locally, we have a company here in LA. They actually make the beryllium for James Webb Space Telescope. So I don't know
Huh.
whether it may be, for your reference. And
That's good to know. Yeah.
yeah, and actually, there's a lot of good things in AIAA, especially in the LA section, so we can chat more about it.
Mhm.
So before we wrap, I don't see more questions, but before we wrap up, I just wanted to know this is very exciting and potentially, AIAA community. There are a lot of people working on those things. Of
Mhm.
course, LA sections especially, but just want to let you know that we just have the AIAA Ascent forum or conference in Las Vegas last month. Is combined with
Okay.
aviation. Then you mentioned your application has space and aviation application, and next year the aviation forum is going to be in San Diego, and Ascent is going to be in Washington D.C. in May. So honestly
Okay.
speaking, some of the people or technical committee, they are preparing, or individual, they are preparing a proposal or paper or exhibition booth for Ascent next year. So if you're interested, the deadline is 18 September next month. So I'll send you some information if you are in a company. For exhibition booth is probably need have more time, but if you want to kind of give a presentation or
Yeah.
paper, the deadline is September 18 next month. I can
All
work
right.
with you and more information about it. So
Yeah, that'd be
yeah,
great.
again,
Thank you.
yeah. Now I have a great idea. Something you can do it for in person here or in AIAA occasions. So I don't see any more. So folks, oh, I see one more gentleman. Mark was saying thank you very much. Very exciting. I'm so excited as well.
Great.
So what I want to say is that this I can chat with you. For example, you mentioned about kind of reimbursement or kind of, just think about it, how much you might need to come to LA, something like that, for a demo or something like that. For going to DC or San Diego next year, I think that's probably pretty, because that's kind of outside my
Yeah.
LA section. You might have to kind of get your company to support that.
Yep.
Okay, so then so I think that's part of it. Do you want to
All
have
right.
some kind of remarks you want to say before we end the program?
Yeah, overall, like, just thank you again. Yeah, I really appreciate the opportunity to speak to everyone. Thank you, everybody, for your participation for coming in on a Saturday, which we agreed is the best time for a meeting like this, but I also understand that it's a Saturday. So thank you for spending your time letting me speak with you. And yeah, I would love to, meet some of you in person, maybe next time, whether it's at a conference or something, or in person for another keynote session. So thank you again. And yeah, that's everything from me.
Thank you so much, Luke. And for folks online, if you look at his bio, Luke's bio, he like to see if anybody can chat with him about surfing. And
That's right.
yeah, you should come to LA. That you can surf every day.
I've tried surfing in LA, and again, I'm a beginner. I just got killed by the waves out there. Right now, actually, in New Hampshire, the waves are pretty good. So I was looking at them,
Oh.
but I think right now they're too big for me. So I still have a lot more practice.
Yeah, actually, we used to do event in Manhattan Beach area, and
Okay.
you can just walk 5 minutes. There are a lot of people surfing, and the surfer will
Yeah,
park the car in that area. That's
that's
a great.
funny.
Yeah, and the bouldering. So if you want to enjoy the bouldering with Luke, that
Yeah,
would be wonderful.
that's right. I would love that. I'm a little bit better at that.
Okay, then you can teach folks here and over there in Maine. That's wonderful, New Hampshire.
There you go. Yep.
Excellent. So thank you, everybody. Thanks, Luke, and thank Gail online for your company and everybody. So wish you have a wonderful Saturday weekend, and I look forward to seeing you next time.
All right. Thank you, everybody. Take care. Enjoy the rest of your day.
You too. Thank you so much.
Bye-bye.
Bye-bye.